in time for the arrival of a huge geomagnetic storm this weekend. That's a storm caused by activity on the sun's surface, like a coronal mass ejection, where chunks of the sun are flung out into space, sometimes towards Earth.
We have a very rare event on our hand. The last time that we issued a G4 watch, which is a geomagnetic storm watch for severe levels, was 2005.
Sean Dahl is a project service coordinator with the National Oceanic and Atmospheric Administration's Space Weather Prediction Center. He kicked off a press conference about the event Friday. The agency monitors the sun's activity, and this week, they noticed a large cluster of sunspots on the surface of our nearest star. With those sunspots came flares that kicked off this geomagnetic storm Wednesday. Since then, there has been at least 5 coronal mass ejections, or CMEs, pointed towards Earth.
Some are catching up with other ones. So our level of confidence is high that we will have an arrival of this CME or the beginning of these CMEs as early as this evening, Eastern Daylight Time, kind of later in the evening perhaps.
Scientists think the storm could last through Sunday.
We have notified all of our infrastructure operators that we coordinate with, such as communication folks, satellite operators, and of course the power grid here in North America. So they are able and prepared to take mitigation efforts as much as possible.
But one good thing about geomagnetic storms is that they can produce auroras, which in the Northern Hemisphere are called the Northern Lights. This storm is expected to be so large that people as far south as Alabama may be able to see these rare auroras. We want to contextualize this weekend storm by sharing the story of the biggest recorded geomagnetic storm to hit Earth and how these storms are made. That storm happened almost 200 years ago, before the American Civil War. Then, the Northern Lights were seen as far south as Cuba. Enjoy the show.
You're listening to Shortwave from NPR.
In 1859, an English scientist named Richard Carrington spent much of his time watching the sun's activity. And in September of that year, he noticed something next to a large sunspot, one of those dark areas on the sun's surface.
He saw a really big flash, and he wasn't sure what happened.
Dr. Samaya Farid is a solar physicist at Yale University.
He thought there was some kind of accident with the instrument or something like that.
Less than a day later, on the other side of the world, a group of gold miners in the Rockies woke up to what they thought was the sunrise.
Come out the tents, and people have started, going about the day, and they realize, wait, the sun is not rising. This is actually just an aurora.
They were seeing the aurora borealis, the northern lights. This aurora was so huge, it was witnessed in places where it's rarely seen, like Cuba. This event even caused strong southern lights in places like Chile and Colombia. And it was doing weird things to the technology of the era. Telegraph machines sparked, shocking operators, catching the telegraph paper on fire, and some of the machines stopped working completely. And in one case, an unplugged telegraph machine continued operating, powered by a rogue current in the atmosphere. What Richard Carrington observed that day taught us a lot about the sun and space weather.
People knew about the aurora, but they didn't know it was related to the sun. So he was the first person to kind of correlate the two.
Today on the show, the Carrington Event. Plus, we'll learn about what's happening on the surface of the sun and what may happen the next time a massive solar storm, like the one in 1859, hits Earth. I'm Regina Barber. You're listening to Shortwave, the science podcast from NPR.
On Wait, Wait, Don't Tell Me, our celebrity interviews aren't quite like anybody else's. For example, country star Brad Paisley has multiple Grammys, but do his teenaged kids like his songs?
So we listened to it in the kitchen, and Huck, my oldest, said, well, they can't all be gems.
I'm Peter Sagal. Join us for the show that asks the questions nobody else seems to want to know the answer to. Listen to the Wait, Wait, Don't Tell Me podcast from NPR.
New from the Embedded podcast. What happens when 3 Republican women challenge their own party?
Maybe we need to speak out a little bit bolder. Maybe we need to do something to get people's attention.
They have a front row seat to democracy. Now, you do too. Listen to Supermajority from NPR's Embedded and WPLN.
Every weekday, NPR's best political reporters come to you on the NPR Politics Podcast to explain the big news coming out of Washington, the campaign trail, and beyond. We don't just want to tell you what happened, we tell you why it matters. Join the NPR Politics Podcast every single afternoon to understand the world through political eyes.
A geomagnetic storm happens when the Earth's magnetic field fluctuates. It changes. It can be generated from the sun's activity. But to understand this huge 1859 solar storm called the Carrington Event, we need to understand two other things. First, solar flares. Solar flares are caused by a sudden release of high-energy photons, which are particles of light, and other high-energy particles from the sun's atmosphere.
And that's kind of the largest type of eruptive event on the sun.
Solar flares release an explosion of mostly electromagnetic radiation. Some of them are white light flares. The photons that white light flares release are in the visible portion of the electromagnetic or light spectrum. But sometimes these eruptions also send matter toward Earth.
It releases sometimes a CME, which is a coronal mass ejection.
These coronal mass ejections, or CMEs, blast hot plasma, superheated gas, from the sun into space at more than 1 million miles per hour.
So the flare is like the bomb going off. And then the CME is like the rocks and the particles and the
like
wave.
A chunk of the sun coming at us.
Right, exactly.
Oh,
so,
wow.
yeah, it's two. Sometimes you can have a flare without a CME, and sometimes you can have a CME without a flare, but they're very also highly correlated to each other. So a lot of times we have a flare, you also have a CME.
Okay, so solar flares are large explosions of electromagnetic radiation from the sun's atmosphere. And you're saying they're sometimes accompanied by these coronal mass ejections, or these CMEs, which are huge plasma eruptions from the sun. So can you tell our listeners, how do these auroras even happen? How do northern lights happen?
So a lot of people think that the particles that are causing the aurora are coming from the sun, and they do kind of indirectly. But really, we have the Earth and the magnetic field, and there's already particles inside of that magnetic field, the Earth just sitting there. And so when those particles and radiation come from the sun and the CME, it interacts with the Earth's magnetic field, causes it to push around all its particles and then push those particles down inside of the Earth's atmosphere. And that's what you see as the aurora.
Right. You're seeing these particles colliding with the hydrogen and nitrogen in the atmosphere. So what do we think happened in the 1859 solar storm, the Carrington Event? Did we see a flare and a CME?
Yep. So we had a CME that happened before the Carrington Event. That one didn't have as much impact on Earth, but people did notice some aurora. And then this flare, white light flare, which means that it was observed in white light. And then the CME that followed that one is what caused a lot of the disruption on Earth.
And not only are we having charged particles coming into our magnetic field, but we're also having a changing magnetic field. And when you have a changing magnetic field, you induce electricity. So that's another reason why those telegraph wires in 1859 got all messed up.
Yeah, exactly. It's overload of electricity generated just from those moving magnetic fields moving quickly and generating electricity, which is nuts.
It is, right? Okay. So, but brings us to because you have Earth's magnetic field changing, your energy grids are getting busted. So what would happen if we had a storm like that now?
Yeah, it's estimated that that kind of event right now will be catastrophic across the globe. That means no internet, no phone, no TV, and no power. And not just that, even the water cleaning systems and health systems, all of those things could be potentially wiped out. Anything with an electrical circuit could be potentially destroyed. Some people have estimated it would take us years to recover, 10 years to recover from one storm like that.
So has anything come close to a Carrington event in recent years?
We have, but it did not impact the Earth. But we have seen white light flares that were the size of the Carrington event. It would have been very impactful if they had been directly aimed at Earth.
These huge events, how often do they happen?
Well, so the sun goes through a solar cycle, and that happens every 11 years when we go from having a lot of flares at solar maximum to not that many flares and solar minimum. But that large Carrington event type storm, a lot of people think only happen, once every 10 years, at least to 100 years. It depends on which estimation.
And the Carrington event happened way back in 1859. So We're overdue.
Past due for one, definitely, by any estimation.
Makes me think of like the big earthquake in Seattle. They're like, any day now.
Yeah, exactly. It's like any day.
Any day. But so what are we doing then? Like, what are we doing to prepare if these events are coming?
Yeah, so I know that there's a council that has been set up that is a collaboration between all the agencies like National Oceanic and Atmospheric Administration, National Science Foundation, and then NASA and Department of Defense, Department of Homeland Security. So I believe that organization is called SWARM, Space Weather Operations Research and Mitigation. And so what it does is develop a strategy and a plan to implement how to prevent having such a catastrophic effect on the electrical system, and then what to do after that kind of event.
So let's say there's even smaller storms, like how much time do we have? What would that warning be like?
Yeah, so if we have a large flare, it's pretty much immediate. 8 minutes is how much time it takes energy to travel from the sun to the earth, which is dangerous because, astronauts and the commercial private space industry is booming now. Also, high altitude flights would be really effective because you could get extra radiation exposure. So that's almost immediate. That's 8 minutes. We don't have very much warning at all. But for the CMEs, for the particles that are coming with the CME, we have about 2 or 3 days warning.
Okay. These coronal mass ejections, they're composed of matter, right? So they're moving super fast, but they're not traveling at the speed of light. So we have more time than a flare. That sounds better.
Slightly better, And we do have now, we have observatories that observe the sun 24/7. The Solar Dynamics Observatory is one of them, and it takes images of the sun every 12 seconds of the whole corona. And so if a flare goes off then, or if we see even a configuration that might cause a flare, they often will put out a flare alert.
What do the astronauts do? What do satellites do? Like, what do they do to prepare?
Yeah, so they have a safety plan. So, for instance, the astronauts have a room on board the International Space Station that has denser walls to protect them from radiation. So they will all go into those rooms. And for satellites that are orbiting the Earth, the plan is for them to turn their electronics away from the sun so that they can miss the highest energy particles. They do have a contingency plan, for these type of things, but it's hard to exactly to predict. But they do have a plan.
So the radiation from solar flares can cause problems high in the atmosphere. And we know that here on Earth, that CMEs can destroy our energy grids. Have you thought about what you'd do if that were to happen? Like, have you prepared?
I haven't. I don't have like a bomb shelter or anything like that, prepared, because I'm originally from Alabama and I grew up in the country. So I feel like if I just had to walk to Alabama or go back somewhere in a rural area and kill a rabbit and eat it, I could do that. I'll be fine.
Okay, we're going from a dark topic, a very apocalyptic scenario, but let's come back to the light, literally, because I love solar physics. How would you suggest everyday people observe all this amazing activity on our sun?
You don't have to do a lot to be able to observe the sun. But one thing you have to keep in mind is that you have to protect your eyes.
Right.
So you can go out on any sunny day and build something called a solar viewer, which will kind of project the shadow of the sun onto a piece of paper. And that's the similar setup to what Carrington used to observe the sunspots. You can do that right now every day. That's what I love the most, just watching the sheer beauty of science taking place in front of your eyes.
Solar physicist Samaya Fareed, thank you so much. Thank you so much for talking to me about everything solar. I loved it.
Thank you. I love it too. It's awesome.